It is September 4th, 2017, and this is episode 78 of the Unseen Podcast. I'm your host, Paul Carr, and joining me this beautiful Labor Day morning for him is Nick Nielsen.
Hello, Nick. Paul, and hello to the Unseen Podcast.
Now, for any more information, go to unseenpodcast.com. You can learn everything about us there. We are the unedited, open participation, unscripted spinoff of the WOW Signal. And I'll put a plug in for our most recent episode when we get to the end of this thing. But today I had scheduled this particular recording session for primarily to support people in Europe and Central Asia and other places, other time zones that are not well suited for our usual time of Friday nights at 10 o'clock Eastern to participate. Unfortunately, and there were some positive response to that, but unfortunately, no one there has been able to make it. So it's me and Nick, who's on the West Coast of the United States. I'm on the East Coast. So the topic that we batted around the topic for our usual month or so, and it looks like what we've settled on is the recent announcement about fast radio bursts, and also the rather lurid media headlines about these fast radio bursts, and also the interesting topic, one that I was hoping that Daniela would chime in on, since it's sort of her area, is how would we tell? There's been a little speculation that fast radio bursts might be the result of an advanced alien civilization's attempt to do cross-galaxy beacons, but how would we tell the difference between that and a natural phenomenon? Since these bursts, although they could very well be natural phenomena, there's reasons why to believe they are. They are probably, there's been some interest because they don't have a clear 100% solid astrophysical explanation for them. Could they? Well, we'll talk about that and how maybe we could tell a signal from an advanced ET versus a signal from a flickering black hole or some other phenomenon like that. So let me give you a little background. Fast radio bursts have been in the news for a while. The first several were discovered at the Parkes Radio Telescope in Australia. This is for two reasons. One is that Parkes is a sensitive telescope. The other one is that it has equipment designed to capture these very, very short bursts. These bursts are on the order of a few milliseconds in duration, a few thousandths of a second. They're highly energetic in that very, very brief time span. The other aspect of these bursts is that they exhibit something called dispersion. And dispersion is basically, as a function of time, a very, very short time, the frequency at which the pulse is detected is changing rapidly. And how rapidly this changes is called the dispersion. If it doesn't change at all, there's no dispersion. And if it changes very rapidly, that is essentially a different arrival time for different frequencies, then that's a high dispersion. And astronomers have long used dispersion as a way of measuring how far away a source is, because the further away it is, the more plasma, to put it very simply, the radio wave has to pass through, and so different frequencies are delayed in different amounts, and they arrive slightly different times. It's not a lot, but if you can, there are some pretty solid theories about how many free electrons you have to encounter in order to be delayed by a certain amount. And if it's not right in the galaxy where there's a lot of uncertainty about how much plasma is right in there. We can make reasonable inference that how far away something is based upon that dispersion, what they call dispersion measure. Now, there had been a number of bursts. The first one was a really, really bright one called the Lorimer burst. A fellow named Lorimer was the lead author in the paper that discovered it. And since then, they've all been less bright than the Lorimer burst, but there have been quite a few observed, and they have been observed not only at Parkes, but also at Arecibo, the big dish dug into a crater in Puerto Rico, and at Green Bank in West Virginia, and also I believe there's been a one discovered at the 100-meter dish in Europe. So these are showing up everywhere. There was, at first, people thought they might be terrestrial interference. We now know that is highly unlikely. People thought it might be low orbiting satellites. We now know that is highly unlikely. But the mystery persists as to what they exactly are. Most of the people I've talked to say they almost certainly have to be astrophysical and not an ET signal. They come now. The reason I should point out, these telescopes, like Arecibo or Parkes, only point at a very, very tiny part of the sky. So small that there could be bursts going off all around, and we wouldn't detect a single one of them, unless it happens to be in that very, very small beam. These are very big telescopes. They have tiny beams, so that they're pulling the energy out of a very small part of the sky. And that's how big radio telescopes work. And Arecibo is a huge dish that can be steered and can be on one source for about 2 hours reliably. And it's built into the crater, but they have a feed that they can move around a bit. Green Bank is another big dish. And they have been I believe it was in 2012, one of these bursts was discovered, and later on it was seen to repeat at Arecibo. And it's called 121102. It's a reasonably bright burst. All the bursts have about the same dispersion measure within a certain range, which indicates that they're about the same distance away. And in fact, a host galaxy has been identified where these bursts are likely to be coming from. It's about the right distance away to have that dispersion measure. The galaxy is a bit odd, but it probably does have a supermassive black hole in the center. And in
the picture of the galaxy that's in the Ethan Siegel article we were talking about before the show started, they have the picture of that part of the sky and then a little blow up window, and it's just a tiny little. Certainly don't know much about that galaxy except from the tiny bit of electromagnetic radiation we're getting from that tiny dot.
Right. It's.
I mean, we can't even tell if it's an elliptical or a spiral or some other non-conforming kind of thing.
Yeah. There has been a number of observations of that galaxy since it was discovered to be the host. One of the things that, if you look on that image that they show there, it's just a dot. They can actually do better than that with enough integration. But last May, it was reported that there had been a concerted effort by multiple radio observatories and also X-ray and gamma ray space telescopes to try to detect X-ray and gamma ray counterparts, since we know that some of these stars that produce powerful radio signals also produce X-ray and gamma ray signals. And interestingly, none was seen. So it's all in the radio.
Do we know Do we know that X-ray and gamma ray signals are as robust in crossing multi-billion light year distances as the radio waves have
Well,
proven to be?
yeah, I mean, we have a lot of detections of extragalactic sources.
From what kind of distances?
Oh, from
Is it
this
like 3 billion light?
from comparable distances, yeah. I mean, it some of them are extremely bright and just light up. But yeah, there's a paper by I'll put a link in the show notes by Schultz et al. It didn't get a lot of attention when it came out last May, but uh, it said essentially that there was no detection of X-ray or gamma ray above background, and there should have been had it been one of the more popular explanations, which is something called a magnetar, which is an extremely high magnetic field neutron star. And that's, I don't believe, if there is a good model of that, I don't think I've seen it, but that explains both the very, very short duration of the bursts, which is a problem. I mean, this extremely short duration means that whatever's happening is happening over a relatively small area. And the other thing is that it's the burst is covering a wide range of frequencies, and it's a lot of energy. And so we would expect to see X-rays and gamma rays even at that distance. None above background were detected, and none with the right timing were detected. So it's based upon some reasonable assumptions about how many photons should be kicked out. How many X-ray and gamma ray photons should be kicked out versus radio photons. The models say there should have been some, and there wasn't. So that's another piece of the puzzle. So what you've been seeing lately now, what happened last week? Actually it was August 26th, and something called an Astronomer's Telegram, which is sort of a very brief article that astronomers write to alert each other of things that are going on on short notice. Astronomer Telegram number 10693, if you want to look it up. A burst was reported, a series of bursts, repeating bursts. They recorded. They had. Oh wait a minute, I'm sorry, that was the wrong number. I have the.
You mean the wrong number for the astronomers and no Telegram?
Yeah, it's 10675. Sorry, yeah. There has actually been another burst detected since then, from the same.
Oh, okay. I'm looking at 10693.
Yeah, 10675. 10693. I think it's the most recent. They did detect it with at Parkes Observatory, something called the Westerbork Synthesis Radio Telescope. I guess that's not really strictly speaking Parkes, but no, the one that's gotten all the news came out on the 29th of August, and it describes events observed on the 26th of August. So this was just last week, and the end of the previous week, that they had observed. They did a series of 30-minute scans, and they detected a total of 15 repetitions, which I think is a record, and 12 in one scan and 3 in another scan, and then 0 for the remaining scans. See that, yeah. That's in table 1 of the ATEL. The energy was varied pretty widely, but the so that was reported. So this thing is pulsing like crazy at various times. In a 30-minute duration, it pulsed 12 times, which is nothing like that's been observed before. But this is the same repeating burster. Nobody knows what it's doing. The energy, I should point out, the total power of these things is extremely high. It's just assuming that it's
other telescopes looked at the source and found it quiescent and nothing's happening?
Well,
at other time? Or is it always putting out like that?
Well, no. See, in their subsequent 30-minute scans, and they did after they detected these bursts, they did 7 more 30-minute scans. They didn't get any bursts.
Okay.
Now you need a sensitive telescope. These with the right equipment to detect these very, very small pulses. They're on the order of a millisecond in duration, and the energy density is pretty high, but a lot of the smaller radio telescopes really wouldn't have much chance of picking them out of the noise because they're such rapid events. You can't integrate like you can with other sources. It shows up, pokes its head above the noise very, very briefly, and then goes away. So it's probably in a heightened activity state right now. They don't know what it is. The media coverage, I thought it was remarkable. I was surprised that an ATEL, there was also an article from Breakthrough Listen, which is a SETI project, and that may have been one of the reasons why it was received so much press attention.
Well, you think Breakthrough Listen has that much reach that just one press?
Well, no, it's just that you can in your headline you can state that these guys are alien hunters.
Right. Okay.
You can use the word alien in your headline,
and suddenly you've got more traction. I get it.
The problem that we have with a lot of these popular articles is that they are crafted to draw eyeballs, right? And we've talked about this before on this show where if you use the words mystery and alien somewhere in your headline.
What's so ironic about this is that we know that for more than a decade, it was completely verboten for NASA to even mention SETI in any budget proposal. Once the program was killed on an official level, of course, there's the private SETI.org institute that continues to do it on private funding. But I have heard astrophysicists and other people in exoplanet hunting and people engaged in all phases of astrophysical research say publicly this is all being driven by public interest in life elsewhere, and even better civilizations elsewhere. In other words, life that we could actually communicate with. So if this is what drives it, if this is what drives the interest, it would be better for official sources like NASA to engage fully and responsibly and in an intellectually rigorous fashion with this public interest than to try to set it to one side. And then while you're doing the stuff that has public interest, the science is going to happen too. I've said many, many times that the more telescopes we have looking for alien signals, the more interesting stuff we're going to find in the galaxy, in the universe. And this is what we're finding with fast radio bursts.
Right. Well, of course, fast radio bursts were discovered not by a SETI program, but this particular organization, Breakthrough Listen.
Right, they're specifically tailored to SETI.
They are a SETI organization. That's their. But they are trying out some extremely sophisticated new methods, and the fast radio bursts give them a good way of validating that their stuff is working properly. It's really it's it's not a drill, it's not a simulation, it's real, and if you can detect it, then you're discriminating very, very short pulses, which is something that they want to be able to do with Breakthrough Listen. So, however, and I think that's all great. I think that's fine. And of course, as you pointed out, the United States government can't fund SETI by law. They can fund astrobiology, but
right.
And in fact, they do. In fact, a lot of the SETI Institute is doing astrobiology and not SETI.
Well, astrobiology actually emerged as a field decades after SETI. I can't say long after.
Yeah, well, it was Sagan. Sagan came up with exobiology.
Exobiology, yes, but that didn't get the kind of traction. Astrobiology, if you actually read the astrobiological journals, they're pretty technical, and it would be impressive enough to a non-specialist in understanding that real science is going on there. I know that sounds hopelessly shallow, but that's true.
No, I think that it is, and there's been a sort of changing of the guard from astrobiology or exobiology, which when Sagan coined the term, there was a lot of head shaking.
Yes, there was.
And that's not real science. And look how dead Venus is. Look how dead Mars is. There's nothing there. Which for a lot of scientists, that was exactly what they wanted. They wanted a dead Mars because they could just go and do their planetary science without having to deal with this question that get pricked up everybody's ears. And so Sagan was actually a lot of what he did was not very well appreciated at the time. But then there's been a change. I think the young scientists I talk to are all fascinated by astrobiology, and they consider it a completely respectable pursuit of time, and NASA does fund astrobiology at some low level. So also other funding agencies do as well. And now Breakthrough Listen, which I talked to at length with Andrew Siemian about on the WOW signal, is funded by a billionaire named Yuri Milner. It's one of he actually has multiple what he calls breakthrough initiatives, including Breakthrough Starshot that I think we've talked about in this show before.
Yes.
And Breakthrough, he's got some other longevity breakthrough work is going on as well. And also there's a Breakthrough Prize. So he's funding a lot of different things, not just SETI, but he committed $100 million to SETI over 10 years, which sounds like a lot of money, but if you compare that to a lot of other research areas, $10 million a year is not a big pile of cash. But still,
but it's a much bigger pile of cash than SETI's gotten in the past.
Yes,
the donations that the SETI Institute has been getting. It's
much bigger.
It's enormous.
And a lot of that money goes to pay for telescope time. A lot of it goes to pay for development of software and hardware to detect signals at those telescopes, and then the analysis that has to be conducted on that after the data. And they collect enormous amounts of data. On this ATEL, I believe they note that they collected something like 500 terabytes, something, or perhaps that was on the Breakthrough Listen release. But they collect terabytes of data in just one observing run,
verging on the kind of data density that's produced by the LHC. So really heavy stuff.
They're scanning a lot of frequencies very, very fast. And so they have, it is. I mean, it's mostly grinding noise, but that the thinking is that if you find anything, it's going to be way down in the noise, and you're going to have to pull it out of there, and it's probably going to take multiple observations to confirm anything, and so breakthrough listen is. I can see why they would observe fast radio bursts, even though what Simeon told me, he thought that they are. He's pretty convinced they're astrophysical, that is, not ET, and but I think it's a very good test of their capability, and but because they are a SETI group, that has sort of raised some eyebrows, and people say, well, here
the alien hunters are looking at it, so therefore
the alien hunters are looking at these pulses. And as Ethan Siegel discusses in an article, there are reasons to believe why they are astrophysical. I think that there are some good arguments for that. For one thing, given the very, very narrow beam width of our most sensitive telescopes, these things, the fact that we've seen any at all, indicates they must be popping off all over the place all the time. In other words, if you could cover a bigger chunk of sky with the same sensitivity, you would see a whole bunch of them.
But let me be devil's advocate on that, and I'm not advocating that FRBs are alien signals, but if it turned out that they were alien signals and they were coming from all over the sky, but all of the galaxies were quite distant, billions of years, so we can see them from a distance, but we can't ever get close up to them, and it doesn't seem we could. That would certainly be the coup de grace for the Fermi paradox. It's not a paradox anymore, because just like we would expect, we would see signals everywhere because there would be life everywhere. If there were life everywhere, we should see civilization everywhere. It just happens to be billions of light years away instead of in our own galaxy. So that is not necessarily an argument against fast radio bursts being alien signals. It could be an argument for them being alien signals. The fact that they're everywhere, because that's what the Fermi paradox would suggest, that you would see it everywhere.
Well, I think that's a good point. The fact that there are probably many thousands, maybe even tens of thousands of bursts going off every day.
That's what you would expect to see in a densely habited universe.
Yes.
It just doesn't happen to be that populated in our neck of the woods in terms of our local galactic group.
It's possible that you could come up with a scenario whereby these things have been going on for a long time, and galactic civilizations. You need a lot of energy. A lot of power to make one of these signals detectable. But if you can squeeze it all into a little pulse, you don't need as much energy. And so, maybe you can store up a huge amount of energy and then blast it, kind of like what is done with a rail gun or something like that, where you store it up and shoot it.
Isn't this what the Benfords argue for in terms of looking for SETI beacons rather than signals?
Yes, the Benford beacons are an interesting case here, and they are relevant. I think that the Benfords argue that it doesn't matter how advanced your civilization is, energy has some cost to it. There's some demand for it, and it's never infinite, right? So there would be the higher the energy requirement, like say announcing your presence to other galaxies, would be you would still want to find some economical way to use that energy to make that announcement. You would not, no matter how advanced you are, it's never free. And in fact, it might be entirely possible that their SETI and METI scientists are just as constrained in budget as ours are, just at a much grander scale. And that wouldn't surprise me at all. But but as long as we're in this realm of speculation, yeah, the Benford beacons are something that, although these don't look uniform enough to be beacons, maybe we're expecting something simpler than we actually would be having.
Well, since we don't yet know the astrophysical process that produces fast radio bursts, once again, highly speculatively, it might turn out that this is the most efficient way to send a incredibly strong radio signal over multi-billion year distances. And if we were to learn that we live in a densely populated universe, but not densely populated galaxies, in fact, these galaxies are separated by billions of light years, this is exactly what you would expect to see. You would expect to see a lot of signals coming from a lot of parts of the sky, and you would have to do it by the means that was the most efficient for producing these incredibly strong signals that can make it over billions of light years and continue to produce them.
Yeah,
and we're seeing them repeated. And I find it very interesting that they're clustered together, which implies that there's a two-stage process going on. There's the underlying process that against which the individual bursts happen, and then there's the individual bursts themselves, which are some sub-process of that process that's going on. So if you're looking at a part of the sky and you're getting clusters of fast radio bursts, and then other times you're looking at it and you're getting nothing, both those processes are not going on all the time. So they're intermittent.
Yeah, and we see other processes like that. So, in fact, the universe is full of things like that, where you get a slow buildup and then something bursts and then it settles down. Catastrophic variables, for example. Now, what we do know, another thing that the repetition tells us that it's not a cataclysmic phenomenon, right? It's not something blowing up, because you get to do that once.
Well, back in the 70s, there was a brief vogue for exploding galaxy cores. Before we know what quasars were, one of the theories were that there was a chain reaction of exploding supernovas in galactic cores. And this theory is no longer, I don't know if there's anybody who advocates this anymore, but it was widely advocated in the 70s. Now we have a better idea what quasars are. We don't need to posit that. But if there were such a thing as massive supernovas that were so close to each other that they set each other off, then you might find something like this. But it would be such a destructive incident that the galaxy that was producing this would all burn itself out and just be a dead husk after that.
Right. Yeah. Well, I think that my fondest hope for this discovery of these bursts is that we have something that is a completely new astrophysical phenomenon. And sometimes we think we've got that, and then it turns out that it's not. For example, when the gamma ray bursts were discovered in the 60s accidentally, they weren't trying to find gamma ray bursts. They were trying to detect the Russians or Chinese performing nuclear tests. The idea, it was a treaty verification mission. It's called the Vela mission. And they got up there and they suddenly had alarms going off all over the place. About once a day, there would be a burst of gamma rays. And it didn't take very long to realize that it wasn't the Russians or the Chinese or the French popping off nukes all the time. It was something astrophysical. It was something that was seen to be more or less equally distributed across the celestial sphere. And it took another 30 years before we had a very good set of observations on these things. And we actually started to see optical counterparts, because for a long time just saw the burst and nothing else. Because they couldn't locate the burst accurately enough. You couldn't get a telescope on it
quick enough to.
those big telescopes, they have extremely narrow fields of view. If you don't know where it is to within 5 degrees, you can't get a big telescope on it. And you need a big telescope to see the counterpart. So it wasn't until we had very accurate location with gamma ray detecting satellites purpose built for that we were able to get to see those counterparts. And now, there's a lot better understanding of, and they're probably not anything exotic. They're probably just really, really big stars that blew up in the early universe, mostly in the early universe, and what they call hypernovas. And
right.
But that took 30, 40 years to figure that out. So we may be at the same stage with FRBs. And
an anomaly is always an opportunity, just as we have with KIC 8462853, if I got the numbers right, Boyajian star.
Yeah, Boyajian.
Okay, sorry.
Or Tabby star for the great unwashed out there.
The number of explanations that have been proposed, there are literally dozens of possible explanations. Many of them have already been ruled out, but it's been a very creative process because people know that they've got to, forgive me for saying so, think out of the box to try to explain this. And we have to do the same thing in trying to explain fast radio bursts.
Yeah, well, there are other fun things like that out there, like Chabelsky star. Right.
That's a great one.
Now, Chabelsky star
recently
doesn't do anything. It just sort of sits there and puts out a weird light spectrum. Whereas Tabby star is constantly doing things. And in fact, about 3 or 4 episodes from now, we're going to have the second anniversary of the WTF paper that came out in the Where's the Flux paper that came out in October of 2015. They'll probably do an episode on that. And the star has been active lately this summer, and they've been able to get new observations of it. And so there should be more information coming out very soon. There were a couple of papers actually last week, but they're not a definitive study of the dips that have been seen lately. So we're still waiting for that. And that could be a little while longer yet. But there have been a lot of things proposed. Almost all the explanations cover some of the bases, but none of them cover all the bases. Because we have both we have a kind of what they call secular dimming, which is a slower dimming of the star, punctuated by very rapid dips. And recently, something called Skara Brae was observed, which was a dip that went on for about 20 days. It was only a 1% dip, but actually 1% is a very large dip for a star that size. And it was almost perfectly symmetrical. And right in the middle of the dip, there was a lot of photometric activity. And then it stopped, and then it symmetrically went back without any. Looks like a perfect triangle almost. This is very difficult to explain, as are pretty much all the Kepler dips.
And these may be multi-decade research programs to puzzle it out. It took that long for quasars. For fast radio bursts and variable, these new kinds of variable stars, if that's what they are, or what particularly we're seeing in Boyajian star, since there don't seem to be any other parallels for it found yet. I suspect there will be, but even if we go to the extreme and we say that the Boyajian star is an alien signal, you would expect to see multiple versions of that as well. No, we haven't found anything close to it, is my understanding.
Yeah, well, there's not a good nobody's come up, to my knowledge, with a good model of how it could be a megastructure and not produce an infrared excess. There have been a couple of ideas that have sort of thrown out there that I thought weren't too terribly bad, but so far, in terms of really modeling it, I haven't seen that. So,
well, like the other explanations, it hits some bases, but it doesn't hit others.
Right.
So,
well, I mean, you would
all of the explanations.
I threw out a speculation about a year ago that it was a giant mirror, and what we were seeing was not so much dips in the brightness, but we were seeing reductions in the magnification of the mirror, and that would imply that the star was much further away than had originally been estimated. Well, then a better distance estimate came out. It wasn't great, but it was good enough to say, well, it's not that far away. In fact, it may even be closer than we thought. So, that kind of rules that out. Even though it's not, it's probably not 100% ruled out yet, but it's very close to being ruled out. So, but there's not, it's certainly not a classic Dyson swarm. It at least as far as we can tell, but we'd never caught it in the act of those really big dips yet. It's entirely possible that there is some kind of megastructure there that when it causes a 20% dip would have an infrared excess, but we haven't seen it, and we don't know why we haven't seen it. If it is there, we wouldn't know why we wouldn't have seen it, even when it's not causing a blockage of the light. So, and there's been a lot of things thrown out there. Planets with giant ring systems, which have has problems. A lot of problems, actually. Comets, not such a great idea. Interstellar medium.
I heard that was definitively disproved recently.
I don't know if definitively, but it's certainly hanging by a thread. The problem is that we did get a good spectrum in one of the recent dips, and there was no change to the spectrum pre-dip and during the dip.
But speaking of the interstellar medium, one thing I was thinking of when you first started talking about fast radio bursts, we know that the stars from the surface of Earth, the stars appear to flicker because our atmosphere is thick and
right.
it changes as we look through it. But when we're talking about distances like 3 billion light years or looking over cosmologically significant distances, presumably there'd be so much interstellar and intergalactic medium between us and any distant source that it would be like looking through an atmosphere, and you would expect to see flickering from that. Is there any basis for that, or is that?
It's not observed like that. I mean, we have a lot of data from Kepler. There's certainly a lot of photometric activity on the star, but the problem is that interstellar medium shouldn't repeat. It should, if you got a cloud on there, it should go by you. And so if you're seeing something that's happening on timescales of days,
right,
that indicates a lot more fine structure in interstellar medium than anyone's observed, and complex structure.
But now I was actually referencing the fast radio bursts, and the Ethan Siegel article we mentioned here says that the third reason why we shouldn't think it's aliens is active galaxies have produced similar radio signals. Flickering, feeding supermassive black holes can cause them. The galaxy housing these FRBs possesses exactly this. So wouldn't we expect to see over a distance of 3 billion light years a lot of variation in a signal anyway, just because there's so much stuff between us and them?
Well, that's what the dispersion is. That's the stuff between us and them. And that's in radio, that's pretty much what you're going to have. These radio frequencies go right through gases and dust. They're not that influenced by it. They're more influenced by plasma, and there is a thin but detectable intergalactic plasma that it is. You got to. The most models have it that it's sort of how much you're looking through is a function of distance. There may be some variations with direction as well, but because if you're looking through a galaxy cluster, it might be denser there than it is out between clusters.
Yeah, I was going to say exactly that. Or you might even get a situation where you get a gravitational lens that's going to influence it.
Right.
Some galactic clusters produce incredibly complex gravitational lenses that give a signal over and over and over from our perception, just because it's coming by different distances based on the gravity between us and the object observed.
Right. Yeah, you can see that, but I and you would see that in radio as well as in optical. But I think they've got a pretty good handle on gravitational lensing. You would certainly see it. I mean, and not only that, but it would not be flickering. It would be very slowly varying, if it varying at all. If you got a gravitational lens today, I can go back and look at it a year from now, or 10 years from now, or 100 years from now. It's going to vary very extremely slowly.
Right. That the time scale of that is so different from human observation. It's essentially static for us.
Yeah. For a gravitational lensing to cause a phenomenon on the order of a millisecond would be something really new.
Right. You would assume that it was produced by the source and not by the lens. Yes.
Now there could be, if you assume there's a supermassive black hole there, that is, there's probably, you can probably come up with a way to get a burst. The problem is, how do you get the kind of burst that we're seeing? And,
right. The burst is just radio waves not attended by the gamma ray bursts and the other.
Yeah. And there have been actually more than one attempt to find counterparts to bursts that have both, at least two that I know of, and they both failed. And one that was conducted at Parkes, they looked at everything they could: infrared, optical, X-ray, gamma ray, ultraviolet. They saw nothing.
Well, hopefully ongoing research into fast radio bursts will find something a little closer to home than 3 billion light years, and we can get some kind of idea what kind of galaxy we're talking about. We know that most galaxies, of course, have supermassive black holes at their center, but like I said, this one is so small and so distant that we don't have much of an idea of its structure at all.
Yeah, well, part of the problem is that many of the earliest bursts, the Lorimer burst, I don't think it's very well located. I think the reason this made such news is that it was well located for the first time among fast radio bursts. Yeah, well, I think they've had about a year that they've known pretty well where the host galaxy is, and but the galaxy is that's rare that they actually have that good a location. In fact, the early ones they don't have that well located. And the brightest one they've seen in the Lorimer burst, I don't believe it's that well located. So, since that's the brightest one, maybe it's the closest one. But
maybe
the dispersion measure doesn't really tell us that. So, it's entirely possible. Has a lot to do with geometry too. How bright the burst is going to be. So, it's because we see gamma ray bursts much brighter because there's a directional component to them. At least that's the current thinking. So I think that there's a lot we don't know, and the trick is to find a counterpart of some kind, and that may be now that we have one very, very well located. We can possibly, the problem is you can't get telescope time for something that might happen.
That is the problem. Well, that's one of the values of the breakthrough listen, is that they're trying to scan massive parts of the sky over a very wide spectrum over periods of time, and that's why they're gathering so much data and to dig into later. And then after the fact, I think you said the Lorimer burst was found after the fact by digging through the data.
Yes, it was, because there is a lot of it, and you have to sift through it carefully to find those bursts. And the impressive thing is that they now have the ability to find so many bursts so quickly in the data, and they have. It's been and they can search over such a wide range of frequencies to find them. So that's there's been a big advance in the hardware and the software, but the main thing now that they have to do is they have to get a big guy, like the Keck telescope, or in a few years maybe the 30-meter telescope,
right,
on that host galaxy, and just dwell on it for a while. When they think there's a period of burst activity, get it on there and just look at and see if you can see anything.
Well, that's what people have been doing with Voyagian stars. As soon as people, there's always people monitoring to see if it's going to vary. And now when it varies, telescopes all around the world swing in its direction.
Right. Now,
and maybe by the time the 30-meter telescope is completed, there'll be enough of a science of fast radio bursts that they can be a little bit more predictable in terms of observation.
Well, they could perhaps, there are some things as targets of opportunity. And you can, you have to, but the thing is, since the burst is so brief, if you say, well, we just saw a burst 5 minutes ago, can you swing over and look at it? They probably won't see anything. But if you say, we're in a period of high activity now, could you spend tomorrow night monitoring the galaxy? Then you might actually get a positive detection. Or even if you get a negative detection when the burst is observed, that's a result. So
the question buried in this discussion of the last few minutes is, how predictable does a phenomenon need to be before institutionalized science is willing to spend money on its observation? Because obviously when the LHC was built, you couldn't guarantee this instrument is going to either confirm or disconfirm the Higgs boson, but you could say that it was going to produce a lot of collisions and that we would see a lot of subatomic particles. And if we do enough of this, we might observe something that was significant to physical theory that we haven't observed before, because the energy levels are far higher than what we've been able to do with smaller colliders in the past. And that seems to me strongly parallel to this. To looking at the sky with telescopes, is there's a level of predictability that people want before they start spending their telescope time on something that may or may not be there.
Right. Well, I mean, they do surveys where they'll look at a big chunk of the sky and try to find new sources when they have a new telescope, and
like the Sloan Digital Sky Survey.
Yeah, or when Palomar, the 200-inch telescope at Palomar was first put up there, one of the first things they did was took a lot of beautiful plates of the northern sky, and they did any proper astronomy library had those plates. They're all digitized now, so you don't need them. You don't need to have the paper printouts, but you can. When I was an undergraduate, we had the Palomar Sky Survey in the library, and you could go there and you could pull out any of the, they were basically just a big piece of paper, like an 11 by 17 piece of paper, and get your magnifying glass out and find any source you want. And you look at it and there'd be all these galaxies all over the place. And that was the deepest we'd ever looked into the sky at that point. And so they'll have surveys, but surveys are guaranteed to find sources. And they're guaranteed to find fainter sources if it's if it's the most sensitive.
Right. I was just going to say, if it's a new instrument, it's just like when people started to first build radio telescopes, they found the low hanging fruit because they found the things that people hadn't seen before. And I in one book I read, they were saying there was a heavy trade in trying to find out the most interesting radio sources for those, so the optical astronomers could point their telescopes in the same direction and were likely to find something of interest.
Right, but for an example, Tabby Star is a good example of how you cannot get telescope time to just monitor something that's not predictable. She was unable to get funding for any of even you don't need a big telescope. You just need a small telescope, a network of telescopes to monitor the star, to wait for it to dip again. Nobody knows if it's ever going to dip again or if it's going to It may dip in 10 years, or it may dip next week, right? So she had to go to a Kickstarter to get about $100,000, actually a bit more than that, to buy telescope time from a private telescope network. And that worked. But she could not go to the National Science Foundation and say, give me $100,000 to monitor the star. We don't know if we're going to see anything.
Unless we saw a real changeover in the people who are on that board and who are interested in taking a different approach.
Yeah, well, they don't like to dedicate time to things that are not likely to be successful, at least on a given. And in fact, I don't know, not everybody knows this, but Tabby's recent proposal for Hubble telescope time was rejected. And
you cut out for a second. What was rejected?
Tabby's recent proposal for Hubble telescope time. Hubble has the remarkable ability to detect ultraviolet light that you pretty much can't see from the ground. And it's quite sensitive in ultraviolet. So the question is, if there is something blocking Tabby's star that is very, very small grain, you should see that in the ultraviolet clearly. And
so did Hubble did the people controlling Hubble reject paid time, or did they reject funding this?
Well, there were two proposals. One was for a target of opportunity, that is, Hubble will swing over there when an event occurs, and the other one was more just a straight observing time. They were very similar proposals. They wanted the same information. They wanted the ultraviolet spectrum, and it was turned down. Now, she believes that what they learned from that will help them write a proposal for next year that will be better and have a better chance of being accepted. Plus, they'll have data from these recent dips that will strengthen their case. So, but the long-term dimming that is being observed now, not only now, but has been observed during the Kepler mission and more controversially in the Harvard plates, has been, we should be able to rule out a lot of theories for that with ultraviolet observations. And over time, it would take observations over a period of months or even years to really make a case for that. But she is, in spite of all the press she has received, she hasn't received a lot of support from the telescope time, the keepers of telescope time.
That's true of most scientists who stand outside the mainstream. They get press, and they can crowdfund things like Voyagian has crowdfunded her research, and Jordan Peterson has funded his research when he got cut off from his grants. But the institutional science does not look kindly until it's well established. And that's unfortunate, because we really need a more pluralistic science and people being willing to risk their careers and stick their neck out instead of making it more difficult for them, make it a little easier for them to risk their entire career on an idea that other people aren't pursuing.
Right. Well, one of the hopes is that next year, NASA will launch TESS, which is a transiting exoplanet survey, and it's multiple telescopes looking at relatively nearby stars, relatively bright stars for transiting planets. And it's going to survey a lot of planets, a lot of stars, most of them nearby. And the hope is that it will detect another Tabby star. And potentially, a dipper like Tabby star that is a main sequence star. If it can do that, then we'll have two examples, and I think there'll be a lot more interest in studying it. And but we don't know if that's going to happen or not. That's now, you can make a statistical argument. For example, with the Kepler Space Telescope, we already knew that there were transiting exoplanets. We'd seen them in ground-based telescopes. But did you know how many we were going to detect? Well, no, but this whole experiment is the number that we detect will give us a sense, will give us some idea, statistically speaking, a census of how many planets are out there and what kind of planets they are. And I think it succeeded at that. In fact, it succeeded at that pretty early on in its mission. So that was...
Yes, and it really, really changed, public scientific discourse around exoplanets.
Now, if you look at it, the periods of the planets that Kepler was able to discover in the time that it was up there were pretty much all less, not, I should say all, but the majority were less than 1 year periods. And a lot of them were just less than a month. So, and that's a discovery bias, because you want to see those repeating. And if you're up there for 4 years, how many repetitions do you need to see? Well, if it's a small planet, you might need to see quite a few, because it's like an Earth-sized planet, because it's a very, very subtle dip and almost undetectable.
Yes. Observation selection bias. So once again, the Kepler got the low-hanging fruit of planetology. Obviously, the first thing being hot Jupiters, which are big, so they're easier to see by the occultation method, and they're easier to detect by the radial velocity method. So you've got two methods, each which can confirm the other, and making it easy to find hot Jupiters before other planets.
Yeah, the size and mass of them and the proximity, because the dip will repeat many times, is in the 4 years that Kepler was up there, and also Kepler did detect a few smaller planets in further out orbits. And
I was just reading last night a 2015 paper about Kepler 452b. Which is a 1.6 Earth's radius exoplanet. I think that had a period of like 285 days or something like that. So it's getting up on there. Not quite a year, but still, you have to hang around a long time to confirm something like that.
Yeah, and in reality, we would need a super Kepler to really catch the Venus and Earth-sized planets in habitable zones around sun-like stars. Or just point it at a place where, like Tesla do, where we'll be able to see more closer stars. We get a better signal noise ratio.
Say close. What's going to be the rough approximation of the scope of distance we're talking?
The distance, I don't have a number off the top of my head, but these are more solar neighborhood stars.
Dozens of light year, maybe.
Yeah, Kepler was a relatively large telescope. This is a series of smaller telescopes that'll be doing a survey. So the brightness of the star that you'll need to have is kind of, Tabby star would be just sort of like the upper limit of what they could reasonably see. So okay. It's not. These are not big telescopes. A lot of amateurs
we need to learn about we need to learn about our solar neighborhood. There's a lot to discover there yet. There's a lot of really suggestive stars like Tau Ceti that are like the sun, and if they have small exoplanets there, that would obviously be of great interest to us.
Yeah, well, the Kepler main mission was focused on a very small patch of sky in one constellation. The Kepler 2 mission, which is currently ongoing, it can only see stars that are close to the Sun-Earth plane, what's called the ecliptic. It can only see, so it's also rather limited in the field of view that it has. TESS will be able to look over a lot of sky. So it's trading off being able to see a lot of sky for being able to get a highly sensitive detection over a small part of sky.
So we have complementary methods that we can balance off each other to get a better sense of what's actually going on.
Yeah,
all of these experiments have strong observation selective effect, and we have to try to work around that to figure out what's going on.
Yeah, also they will need with tests they'll be looking a lot of red stars for planets because these smaller stars will have bigger dips percentage wise. So
K and M stars, presumably.
Yeah, a lot of that will be. That's where they think they're going to have the most success, but we'll see. It'll be interesting to see how closely the detections match predictions, and we'll get a good census of nearby stars with that. And also the Europeans are working on a similar mission. It's a few years behind, but it's called Plato, which will have a similar approach, looking for transits. And Plato will focus on sun-like stars, so that should be a really interesting census as well. And I would hope that they would be able to tell us if we got how common planets that are underneath the frost line, but above the, what we call the habitable zone, which is, where we don't either burn or freeze, essentially, at a distance from the star, that we can probably hopefully get a lot of smaller planets in that zone and get a good census. Because Kepler gave us a pretty good idea, but not, I think we'd like to see more.
Definitely would like to see more. And more powerful instruments, more money spent on science, all of that good stuff.
Yeah, you can go to exoplanet.eu and actually plot some of the parameters of the different exoplanets that have been discovered and how they've been discovered and so forth. So it's you can pretty easily explore for yourself what those numbers look like. It's kind of fun to go there. I'll have a link to that out in the show notes. Okay, Nick, I think we're going to wrap up. I think we'll skip the recommendations this week, but we're going to have those back next show, episode 79, which will be in less than 2 weeks from now. And it'll be a week from this coming Friday. And that will be, again, the topic for that one is still wide open. So if anybody wants to come over to our Google Plus community and weigh in on topics, you don't have to be on the panel. Just what you'd like to hear about, what you'd like to see discussed. We'd love people to come over and do that. You can also email unseenpodcast@gmail.com if you have something that you are interested in that you'd like us to cover, or questions or comments or snark, whatever. Also, you can go to the blog. It's called unseenpodcast.com. And for each episode, there is a blog entry and you can post your comments there. And so there's lots of ways you can get in touch with us or communicate with us. And we like to hear that. We like to see what people are interested in and what makes them want to listen to a whole show, or what they thought what the weaknesses were. I'd like to know a lot about that. And so thanks for listening. Thank you, Nick Nielsen.
Thank you, Paul. It's been a pleasure.
And this has been Unseen Podcast episode 78. And we'll be back in a little bit less than 2 weeks with 79. And go to unseenpodcast.com for all the information you want about the show. And that's it for me. My name is Paul Carr. Music has been by DJ Spooky. Goodbye.